Sorry for the inconvenience. Yeah, so let me restart since it's the first slide. Yeah, so our team solution is based on a retriever reader framework. Yeah, so for the retriever component, it's basically we built a retriever mechanism based on a stem corpus, and the purpose of this retriever is to find some helpful text snippet that would assist the MCQ model to help answer the MCQ questions. Yeah. So next, I would explain in detail what is the retriever and what are the components. Yeah. The critical factor of getting a decent solution was to have a high quality stem corpus. So at the start, we explored several open source solutions for this one, but we quickly realized it has some issues, particularly regarding the numbers, equations, and symbols. Most of the time, these components weren't extracted properly, but based on quick EDA, we found that these are quite important detail to have in our solution. And also Wikipedia is quite huge. So we focused on filtering out the relevant articles only. Yeah, so to this end, we explored the Wikipedia category graph. At the start, we defined some of the relevant categories that we were interested in for this task. Some examples would be concepts in physics, physical quantities. So we defined a set of seed categories, and then we recursively crawled Wikipedia up to a certain depth, and we extracted the member pages as well as subcategories. Eventually, we ended up with around 500,000 Wikipedia articles. Yeah, then we use Wikipedia API to extract the details of these pages. Yeah, once we have this data set, we proceed to chunking because some of the pages were quite long. For chunking, we first split each of the article into the sections, and for the longer section, we furthermore split them into chunks of roughly 300 tokens. Yeah, so these were the hyperparameters while creating the stem corpus. One of the important detail was we maintained two representation for each chunk. One was a short representation without any overlap. We use this to embed and search. And another one was the same short representation, but we also tracked the previous and the next chunk in a way to make a continuous span. And this longer representation actually boosted performance of the downstream MCQ models. Yeah, so when we start, we explored several retrievers from the MTEB leaderboard. We found that the pre-trained model already had quite strong performance, but we explored also fine-tuning of these embedding models, particularly for this STEM domain. Yeah, and it was nice that we already generate synthetic data to train the MCQ question answer model, and we could repurpose the same data set to fine-tune the retriever. As you can see that there would be a context snippet from the Wikipedia, and there would be a generated question based on that. And this would form a positive pair to train the retriever. And this actually helped to do two things. One, to reduce number of snippets that would be provided to the downstream model, and also boosted the performance. So at the start, we did some experiment, and we found that this was helpful, and we kept this one as a part of our final solution. And we also explored re-ranker training because we found some of the retrieve context is noisy, meaning it has some very short text, and it is not quite related to the question that we want to solve. And having the re-ranker actually stabilized our solution. And finally, we provided top 2 to 4 re-ranked context to the downstream model. Yeah, and now coming to the downstream model, we explored several solutions. Firstly, we did a span classification model. It was quite nice because we could format all of the 5 options into one input text. So basically, the prompt is the question, and context is the retrieved text snippets from the retriever mechanism. Then we just concat 5 options into one input text, And then we did mean pooling of each of the options text, and we got the representation for each of the option segment. And finally, we did multi-output classification. So this way, it helped us to have the cross-option information. And this formulation, actually, we didn't have the position bias issue. Next, we also had the standard auto model for multiple choice. And this one, we explored several backbones, particularly Jupyter was quite helpful. And finally, towards the end of the competition, we realized that we hit a performance ceiling using just Jupyter model. At that point, we explored fine-tuning of large language models. And we did fine-tune Mistral 7 billion model with LoRa settings, and it actually boosted our performance in ensemble. And it was still quite not enough to catch up to the top teams. So finally, towards the end of the competition, we decided to explore zero-shot question answering with 70 billion models. And there were several public notebooks. So we did some quick experiments. And for this one, we run top 5 to 10% MCQ based on the entropy. So we selected the questions which were like ambiguous for rest of our models. And these models we run through the 70 billion model, and it actually gave a strong boost to our performance. Yeah, and all of these 4 types of fine-tuned model were part of our final solution, and which helped us to secure 6th position finish. At the end, I would like to mention that our team was quite diverse based on country of residence as well as the company we work for. And it was quite exciting in terms of collaboration. And the problem was quite nicely set up from the Kaggle side. So we enjoyed a lot in participating in this competition, and we learned quite a lot throughout the journey. Yeah, thank you.